Here we're looking at the free radical substitution reactions of alkanes. Considering the nature of free radicals and their reactivity, and the individual steps in the mechanism of the free radical substitution. A radical has an unpaired electron. That's a definition. Radicals are highly reactive. Radicals are extremely reactive and will rip an extra electron off any other species it collides with. So here, I'm seeing a chlorine molecule, Cl2, with my covalent bond between the chlorine atoms. That bond breaks in this reaction. Each chlorine atom that originally formed the bond comes away with one electron, shown simply as a dot. Now, a free radical is a species with an unpaired electron again, and that's our definition. It's shown by the dot beside the symbol. They are the most reactive species in chemistry. Free radicals are formed by homolytic fission of bonds. Let me stop there and look back at the chlorine molecule. It broke. The two chlorine atoms that made the bond came away with one electron each. Okay, in homolytic fission, one electron from the shared pair goes to each atom. Homo always means the same. Fission always means to split. Of course, each chlorine atom also has 3 pairs of electrons, but we don't show these. It's the unpaired electron that makes the free radical, any free radical, so reactive. Notice that the single-headed arrow shows the movement of one electron. I'm back to my chlorine molecule in the beginning. Single-headed arrows in red showing one electron going from the bond to a chlorine atom. Very important if I'm using what we call curly arrows to show the movement of electrons, that they start where the electrons start and they end where the electrons end. Let me just also add, almost as an aside, a double-headed arrow would show the movement of 2 electrons, and that's much more common. UV light and heat are both forms of energy. Each can be used to break bonds. And that's why originally the chlorine molecule had its covalent bond broken, because either UV light or heat was provided. Now, if you can remember the hydrogen spectrum, the most energetic transitions for electrons were in the ultraviolet. Makes sense that UV light would be of the right energy to drive an electron out to the outermost shell and then a little bit beyond. That means the electron's gone. Same with the electrons in the bond. Free radicals are formed by homolytic fission of bonds. In homolytic fission, one electron from the shared pair goes to each atom. And the formation of free radicals is the first initiation step in a reaction involving any compound containing carbon and hydrogen. As an aside, CFCs, chlorofluorocarbons in the atmosphere, break down to release chlorine free radicals but not fluorine radicals. Their molecules involve carbon being single bonded to chlorine and fluorine. Chlorine atoms are larger than fluorine atoms. The CCl bond is longer and weaker than the CF bond and breaks more easily. It's UV light in the atmosphere that causes the CCl bond to break. UV light causing the bond between 2 chlorine atoms to break in this mechanism. My highly reactive free radicals start a chain reaction during substitution reactions with alkanes. A mixture of products is formed. This chain reaction has 3 stages. We've already looked at initiation, propagation. To propagate means to grow. This is keeping the reaction going. And termination. The initial reaction involves forming the chlorine free radicals. 2 propagation reactions involve the formation of a methyl free radical and the regeneration of a new chlorine free radical. Here, I've got a chlorine radical colliding with a methane molecule. Remembering that that chlorine radical is highly reactive. And as I've said already, will rip an electron off anything it encounters. The chlorine free radical removes a hydrogen atom from the methane. That hydrogen atom only needs to bring 1 electron with it to form a new bond to the chlorine, and so 1 electron is left behind on the carbon atom. A new free radical is formed, this time a methyl radical. If we look at the bond C to H, 1 electron forming that covalent bond went between the hydrogen and the chlorine free radical. The other electron provided by the free radical, I get HCl. 1 electron left behind, I get my methyl free radical. And this is the first of 2 propagation steps. If the methyl radical hits a chlorine molecule, and of course that's something very likely to occur, the following can happen. The methyl free radical is now taking a chlorine atom and an electron to make a new covalent bond. Chlorine free radical is regenerated. Summarizing this below, and this is the format that would be looked for if a mechanism for this was called for. The methyl radical takes 1 of the chlorine atoms to form chloromethane, which is the final product, but in the process generates another chlorine radical. The new chlorine radical can now go through the whole sequence again, and at the end will produce yet another chlorine radical. And so it continues. We have a chain reaction. What's produced at the beginning is regenerated at the end to keep the reaction moving. Termination reactions involve removal of free radicals when they collide. There are 2 free radicals, and so 3 possibilities, and all of these happen. I can get 2 chlorine free radicals meeting to form Cl2. I can get a methyl free radical and a chlorine free radical meeting to form CH3Cl, and interestingly, I can get 2 methyl free radicals meeting to make C2H6, which is ethane. Traces of ethane in the products of the reaction provide evidence for this mechanism. Yeah, how is ethane, C2H6, going to get made when we start with methane, 1 carbon, and chlorine? That's very strong evidence for this mechanism. Of course, it's possible for a methane molecule to have more than 1 hydrogen substituted. The mixture of products inevitably formed will include chloromethane, dichloromethane, trichloromethane, and tetrachloromethane. And those products can be separated by fractional distillation. Small point, but if CH3Cl is the desired product, the reaction is carried out with excess methane to minimize production of the other possibilities. If I want CCl4, excess chlorine is used. And interesting, and of course predictable, another halogen, bromine, will react in the same way as chlorine. Any alkane can be halogenated in this way. I have a summary, and the equations are what we might be expected to reproduce in an exam. My initiation. Chlorine, absorbing UV light and producing 2 chlorine free radicals. Propagation. My methane being hit by a chlorine free radical to make HCl and the methyl free radical. Second stage of propagation, methyl free radical combining with a chlorine molecule to make the product CH3Cl and regenerating the chlorine free radical. Termination, any combination of 2 free radicals meeting. Could be 2 chlorine free radicals to make Cl2, could be one of each, a methyl free radical meeting a chlorine free radical to make CH3Cl, or it could be the 2 methyl free radicals meeting to make ethane. Carbon to carbon and carbon to hydrogen bonds are short and so strong, and that makes alkanes very stable. Very little difference in the electronegativities of carbon and hydrogen, and so the bonds are essentially non-polar. That leads me to say, alkanes have short, strong bonds and are non-polar. They are kinetically stable. They will burn in exothermic reactions to give products that are more stable, yet they are thermodynamically unstable. They're very unreactive. This reaction produces polar and much more reactive halogenoalkanes. That's what makes this reaction very useful. Let me remind you of one thing. I'm doing this quite deliberately at the very end. UV light is needed as a form of energy to break the chlorine bond. That's initially. I'm going to put this in red because it's something that people inevitably forget. Oops, not A R A S. Finally, one question based on past paper questions I've seen set over many years. Suggest a mechanism for the chlorination of methylpropane, and it gives you a formula and it says 4 points, and that formula is off-putting. I guarantee there will be people facing this question who very well know the mechanism for the free radical substitution of methane, but now we're being asked to apply that to a very, very different scene, a different molecule. Of those 4 marks, there will always be 1 for initiation, only 1 step in initiation, 2 for propagation, 2 reactions, and 1 for any of the 3 reactions that are involved in termination. I would always go for the first one. Now, I don't really care about the backbone of that molecule. What I know is that I'm going to have a free radical generated from it. It'll be represented by a dot. Our hydrogen will be lost, and it's going to be somewhere. But first off, let's get the easy one. Initiation. Chlorine molecule forming 2 chlorine free radicals. I've got UV light over the arrow to show that UV light is necessary. 1 point. Propagation. I start with that molecule, and I'm going to attack it with a chlorine free radical. Now what I know is the chlorine free radical will rip an electron off and take a hydrogen with it and make HCl. That's the easy bit. The bit that looks hard really isn't. What's left behind has got one hydrogen less. I start with H3 at the end and now H2. And there's a dot there to show that it's a free radical. Honestly, when I wrote this question, I just copied the structure given in the question and pasted it here in the first of the two propagation steps. Then I copied it again, took off a hydrogen, went from 3 at the end to 2, and stuck a dot there to show the unpaired electron in a free radical. Second propagation step, that same structure, for me making this copy-paste, went here and reacted with another chlorine molecule to generate what would be the final product and regenerate the chlorine free radical. 2 marks for the 2 propagation reactions. Termination, any combination of 2. 2 chlorine free radicals, 1 chlorine free radical and the organic free radical, and the organic free radical doubled. And that's it. First time I wrote this question down, I wrote down for the bromination of methyl propane. That would expect people to realize that bromine would react in exactly the same way. Br2 gives me 2 bromine free radicals with their unpaired electron shown. In fact, if I wanted to change this mechanism for bromination, all I would do is change every Cl for a Br. But those are the 4 points. That's it. If you found this presentation useful in any way, please hit like. Please subscribe to be informed of more content.